purpose of this video is creating a function which approximates a graph given several points on the graph. I'll start out by going through a simple example of how this works and then a more complex example which a friend gave me. So if we have a basic graph, something say like this, then we can approximate this by first realizing that it looks something like a cubic graph. So that would be in the form of y equals ax cubed plus bx squared plus cx. The challenge here is finding what a, b, and c are equal to. Here though, we can look at the graph and find points on it, and then using at least 3 points on the graph, we can find possible values for a, b, and c. So we have 4 points here, but we only need 3. This works best if the 3 points are fairly evenly spaced apart on the line segment that you have. Let's choose the points 2, 5, 6, 6, and 10, 8. Using the first point, 2, 5, we find the equation when x is equal to 2, y is equal to 5. 5 equals a times 2 cubed plus b times 2 squared plus c times 2. Using the second point, we have 6 equals a times 6 cubed plus b times 6 squared plus c times 6. Now we have 3 equations and 3 unknowns, so this is actually possible to solve. Now there are a couple ways of solving this, but the easiest way for larger problems is by using matrices and doing row reductions to them, especially because we can use online matrix calculators. So turning this into matrix, we now have matrix. So now we need to do the row reductions on that and calculate what that is equal to. After plugging these values into an online calculator, I find that this reduces to the matrix. So this means that A is equal to 13 over 320, B is equal to negative 7 over 10, and C is equal to 299 over 80. Now we can graph this equation, y equals 13 over 320x cubed minus 7 tenths x squared plus 299 over 80x, and see how close it is to the actual equation that we were looking for. You can plug these values in, and you end up with a graph that looks roughly like the graph that we had. Now, because we didn't put in the exact points or as many points as we had in that graph, we do end up with some discrepancies. For instance, over at 0, it goes through 0, 0. This method is great for graphs that go through 0, 0 and then have other weird stuff going on it. So for in this case, the values that we had, 2, 6, and 10. So you can see at the x value of 10, we have a y value of 8. At the x value of 6, we have a y value of 6. And at the x value of 2, we have a y value of 5. Using the same method, we can do significantly more complex graphs. Again, they aren't going to be precisely what we had, but they will be fairly close. The graph that I'm trying to approximate is this one, namely the 50th percentile line on this graph. First thing, I'm trying to figure out a good approximating graph for this. The more variables you have, the more points you can put in, and theoretically, the more accurate the graph will be. However, there is a distinct limitation in this, in that you cannot reasonably use an online calculator that I was using with numbers larger than 70 to the 5th power. So keeping that in mind, what I will use is the formula y equals ax to the 5th, that's going to be the highest value, plus bx to the 4th, plus cx cubed, plus dx squared, plus ex, plus f. And now, because I've run out of the exponentials, and this looks like a logarithmic function, I'm going to have fln of x. With these, I now have 6 different variables that I can work with. With those 6 variables, now I need to find 6 points. So here we have 7 different points, and we need to use 6 of them. The point that I'll cut out is 2015. So now we need to turn all of those into a matrix. So the first equation that we have will be 8 equals a times 12 to the 5th plus b times 12 to the 4th plus c times 12 cubed plus d times 12 squared plus e times 12 plus f times natural log of 12. Using that same formula, we can find all the other equations. Now that we have all 6 formulas for the 6 variables, we can write out a matrix to describe all of these. Rather than writing that out, I will simply calculate it and then input into the calculator and show the fully reduced form. As you can see, we didn't exactly get nice numbers, but we do have numbers. So now all that we need to do is plug these numbers back into the equation, which, as a reminder again, is right up here. So that y equals a x to the fifth plus bx to the fourth plus cx cubed plus dx squared plus ex plus f natural log of x, with these values for a through f. And we should get a fairly good approximating graph. So I'll do that now. We get the following graph. If you look at the graph that we're actually trying to approximate, you can see that this is a fairly close approximation. Now, admittedly, the previous one was always strictly concave down, so it didn't have any little dip downs like this one does. However, despite that, you can see that it's fairly precisely fitting the previous graph. And if you were to calculate it, you would find that at 40, you had the exact value of 24. At 30, you had the exact value of 21. All those specific points that we have, it's guaranteed to go through all of those points. So there you can see the method that I used to approximate a graph given certain fixed points on it. If you more accurately approximated those points also, you could get a more accurate graph. So that's the method that I used. Hopefully you enjoyed the video, and if you have any other mathematics questions, please leave them in the comments down below.